Alright, welcome back. Let's talk a little bit more about some of the theoretical aspects of the philosophy of measurements. Let's say I have two weather stations up here along this ridge line, and I'm trying to figure out which part of the ridge line has the greatest winds. So I put up these two anemometers, and they both radioed in that the wind speed at the current time is 9.1 meters per second. Does that mean that those two observations are the same? Well, probably not, because see, it would appear that the precision of these instruments is only to the nearest tenth of a meter per second, and that means that we don't actually know finer than that what the wind speeds are doing. But you know who does know? The angels. And they are looking down from above with this cheesy, see the rays of sunlight coming in? Oh. And the angels can look down from above and they could say, no, maybe it's God. No, the one on the left was really 9.051 meters per second. The one on the right was really 9.148 meters per second. They are not the same wind speed. You would actually capture 3.2% more power at the site on the right, because power is to the third power, the power captured by the turbines to the third power of the wind speed. But see, there was no way for us mere mortals down here with our plastic wind instruments to have known this. The precision of these instruments was too poor. I wasn't able to know that. In fact, I do have different answers here. Now, if I could get some more expensive weather measurements that measure to, say, two significant digits, good precision of up to 1/100th of a meter per second, like those sonic anemometers had, now I can see, oh, look. See, even if the real wind was 9.01 meters per second, well, at least that one on the left is telling me 9.05 meters per second. And now my one on the right, well, it's going to tell me 9.15 meters per second. Oh, I can see to the resolution of to the precision of my instruments that the one on the right really has better winds, and I have made a wise choice. The precision of the instruments mattered in making the right choice here. Now, suppose at this time here, I've got some observations, and I really paid some money for some anemometers that report back the wind to 3 decimal places. And I got a report that the wind on the left there is 9.051 meters per second, and the wind on the right is 9.148 meters per second. Are we sure that that means that the location on the right is windier? Well, you can see that's a trap, right? Maybe this is not right at all. Maybe there's a problem with the accuracy. There's absolute calibration problems here. But you know who would know that? That's very hard for you and I to know. But the angels can look down from above. Again, we got the rays of light shining in here. Oh, and they can look down from above and say, you mortal with your imperfect knowledge, the one on the left, yeah, it has a small calibration problem, but the one on the right has a big calibration problem. Or maybe the angels would look down on us poor mortals with pity and say, the one on the left is a high quality instrument, trust its observation. The one on the right was cheap. Its observations are far off. Okay? There's no way for you and I to know that. We'd have to have spent money and get higher quality equipment with better accuracy, or with the luxury of time and support and so on, you could actually maybe figure out that there was a calibration error with one and the other, and maybe even correct for it by, you know, figuring out what you have to subtract from the observations to make them more accurate. But that's going to take time, money, support, etc., things you may not have. Us mere mortals, we just do what we can. But a higher power than us would look down and say, no matter what you are doing, mere mortals, you need to know information about the resolution, the accuracy, and the precision of your equipment. And you're going to need to know about how representative your site is before you make any big decisions about where to build this wind farm. Alright, hopefully not being too sacrilegious on that point. Let's turn to one more idea in our ideas about wind, about the philosophy of measurements. We've actually dropped these words a couple of times already: bias and scatter. The reason why I want to spend some time on this is because when I read page 35 of your book, it seems that there's actually a couple of misprints. And let's get this straightened out real quick here. Let's say that you've gathered a whole bunch of observations of some meteorological parameter, like temperature at some given time. Now, for a variety of reasons, let's just say over a burst of, a few seconds, you gather a whole bunch of observations from there using your instrument and the data logger and so on. We'll learn about how you do that here. All right, so you've got a whole bunch of observations, and for a variety of reasons, the observations are not all going to be the same. It seems like if you had some kind of instrument that was measuring the temperature right now, if you measured it, say, 20 times over the next 10 seconds, you would think they'd all be basically the same, but they won't be. There'll be little fluctuations in the instrument that is doing the measuring. Most of those instruments produce some kind of voltage signal that a piece of electronic equipment measures, and there's fluctuations in noise in the line and so on. All these observations are going to have some spread. And now your textbook actually had a very similar book. Figure, I made this one myself. But let's say we had 4 different instruments that had made these measurements, A, B, C, and D. And let's say at the present time, the real temperature, again, if the angels could look down and tell us, the real temperature is 10 degrees Celsius. So I've got a line drawn in there. All right, each of those instruments, in this particular case, just with the Excel spreadsheet I made 14 observations in a little burst of observations. And you can see that there's a problem with all of them. Instrument A was not very accurate. None of its observations are around 10 degrees Celsius. And so there is this very large bias in the observations. Clearly this instrument is not well calibrated, and well, with time and support and so on, we could probably fix that or correct for that. But like B, that instrument, well, it has a much smaller bias. I mean, those observations are actually pretty well calibrated, but it does have a problem with scatter. Clearly, this instrument has random errors. Over the course of a few seconds, it took 14 observations of the temperature. The temperature did not really vary over 1 degree Celsius. Clearly, we have some problem here with like noise in the line or a low quality sensor or something like that. Well, again, with time and averaging, we might be able to fix that problem. C is an interesting instrument. It doesn't have very much scatter at all. Its 14 observations are all right around 13 degrees. Sadly, that's nowhere near the real temperature. Clearly, there is a calibration problem. Again, with time and energy and some financial support, you could fix, or correct or whatever. But it's got a large bias and small amount of scatter. In contrast, instrument D, which probably cost a fortune, has very little accuracy problem, very little bias, and it has a very small scatter to its observations. Oh, well, those actually look pretty good. I see. So bias is about how the average observation that's taken by this piece of equipment varies from the real or accepted value. Scatter is about the range of values that are being observed under these exact conditions, where the range is just due to mechanical or electrical or whatever noise in the system. We'll learn more about how these instruments all work in coming lectures, but we need a way to quantify this. If we were going to quantify the bias, okay, we could compute the average of the observations, which we're going to be giving in this textbook with the symbol mu, and then subtract off the accepted or correct value, and that difference between the average of our observations and the accepted value would be our bias. Or we could quantify the scatter of the observations by computing the standard deviation of the observations, which your textbook is using the symbol lowercase sigma. Okay, again, we'll learn later about how to actually do that, compute the standard deviation and so on. Plus, there's this Energy 301 class that I'm sure you'll all take, and we learn those kind of techniques there. But here's the deal. As most of you, I think, know, I have an undergraduate degree in statistics, and this just angers me, because this is not actually correct. The symbol mu is actually for mean, which is not the same thing as average. What you want is bar, like temperature bar, T-bar. And sigma is a symbol for standard deviation, but that's not what you're computing here. You're computing the sample standard deviation, which is an S. This is a mess, okay? But I'm going to not be a pain in the ass about this mess, excuse my French. Rather, you wait until Energy 301, the modeling electrical load and yield / statistical meteorology class, where you will learn more about why this is different, why that matters, etc. But I will bite my tongue and use their terminology and their symbols because it's useful to use that in this book. And frankly, it doesn't happen that much in this book. All right, and I didn't realize at the time that I just made that as a word bubble with the God font coming from me. Anyway, all right. That wraps up this lecture about the philosophy of measurements. Let's do a couple quick questions just to make sure we understood what we saw. Question 4. If a weather instrument gets out of calibration, you'll notice an increase in the blank in the observations for that instrument. Bias, scatter, precision, resolution. Which one increases if the instrument gets out of calibration? Make a choice from those 4 options and get some feedback before you move on to question 5.